when you do design of experiment, when you use any software for design of experiment, you also see something called F value, the F value or F ratio. So F ratio of F value is basically what we call the ratio lah. F value is basically, we can say is like this. F value is the difference between group variation, between group variation. I will explain later. Within group variation. Okay, when we talk about p-value, it's just a probability. But when you compare different result, for example, let's say you have two class of result, two factors or whatever. Normally in term of experimentation, it's about factors lah. You have many factors, right? You want to compare between this. Okay, so when you have a group, for example, you have some group like this. For example, you have group of data set. Let's say 1, 2, 3 here. You have one group of data. So you can find the standard deviation inside this group, whatever. Let's say you have multiple groups. Let's say you have this multiple groups, and then the data inside this thing is different. I mean that the spread is different. So this is what we call between group. Okay, this is what we call between group data. Within it is basically within. This is within group. Okay, what they compare, actually they compare the means, the variance or whatever lah. They want to compare the means or the variance, either within group and the between group. So the F value or F ratio is basically the division between this and this lah. We will not go in detail, but enough for you to understand. In order to calculate F value, you need to have this between group and within group. Okay, and this normally needed F value, you will get it when you perform ANOVA like that. ANOVA. So when you want to perform ANOVA, you must have between group and within group variation. In order to ANOVA is there lah. That's why later on in the in our practice this evening, we will show you why for the factorial design you need to select something in order to get ANOVA. In RSM, you don't need to select anything. You put your result, you click ANOVA, the ANOVA is there. But if you do factorial, it's not like that. Factorial, you need to select first, and then based on the selection, because when you select, you basically separate between group variation and within group variation. So you get the and then you get the ANOVA. So maybe not clear now. You will see clearly when we do factorial design later on. I will come back to this F value lah to explain to you why this matters. Why for factorial a little bit different than RSM, meaning that the way how you start the analysis, you need to do some selection in order to get F value, in order to get the ANOVA analysis, in order to get ANOVA table lah. ANOVA table. ANOVA stand for analysis for variance lah. Analysis for variance lah. So you will heard this term again and again. When you perform DOE, the main idea is that they want to perform ANOVA. They want to perform this analysis of variance. Only after they do this analysis, then they can say your sample is significant or not. So that's basically the idea of F value lah, the main idea. The detail I think I will not discuss here lah. So basically, let's recap for a while. When you do hypothesis testing, because after all, when you do experiment, when you put into statistical software, what you do is basically you do hypothesis testing. When you perform hypothesis test, hypothesis test, we have learned before the null hypothesis or not hypothesis. This is just recap. You use a distribution like what, like t distribution, like normal distribution, or T distribution. This when you do sampling, distribution, okay, when you, okay, and then from this from this normal distribution and T distribution, what you will get is that you will get the area lah. You will get area of probability. Okay, so area lah, you get some area. Okay, so this area allow you to calculate probability lah. Calculate probability, and then from this you will get p-value. Okay, when you get p-value, you can tell result. Either your result is significant. For example, you want to check the interaction between factors. So you take that between factors, and then you put it in the normal distribution. This a software did lah. They sort of like distribute it in the normal distribution and find the area, and then calculate from the area, you get the p-value, and then you get the result. So the result either significant or non-significant lah. Non-significant. Okay. So from this significant, whether significant or non-significant, you can sort of like say whether you confident or not with your result. So normally that's why when you do ANOVA, you want the model to be significant. When you say the model is significant, meaning that whatever experiment you do have some effect. For example, this let's say you do experiment, and then you have response, and then you have factors, and then you have noise also. The idea of doing experiment is that you want to sort of like say that these factors affect the response. Okay, the null hypothesis for the experiment, no effect. So that is null hypothesis for the doing status quo, no effect. So alternative hypothesis, if you forget about this null or alternative thing, just refer to my previous video lah. The alternative hypothesis is they are effect. The very reason you perform the experiment, you put factors and response, is that you want to sort of like reject this. The null hypothesis. You want to reject this thing. So rejection of null hypothesis coming from this probability. So if let's say your what we call your graph or normal distribution, your whatever your result, your factor interaction or whatever lies away from the normal. For example, this is basically, let's say this is confidence of interval, the probability. Let's say this is normal. So let's say you put normal situation is 95%. For example, you said the region that's covered 95% of time is normal. So let's say 95%. Let's say you put the normal region is 95%. You put the constraint. So if let's say your result yield here, then it's abnormal lah. When it's abnormal, then when this is abnormal, then you basically you say that there are some effect. By right, they are no effect, normal. But if there is abnormal, then there are effects. So you reject the null hypothesis, and that's the reason why you can say your test significant and not significant. So that's the thing lah. Okay, when you perform this, what we call the experiment, you put in DOE. Not only they tell you about your data, DOE also can predict. Okay. Make prediction. So let's talk about something about prediction. What is prediction? Because I want to talk about prediction because I want to discuss a little bit something related to residual. Okay, you will heard about this word residual when you dealing with the DOE. Okay, residual, regression line, and also R squared, something like that lah. You will see this again and again when you put your data, when you try to analyze your data in DOE software, whatever software lah. Even if you use Excel, you will see this thing. So this have to do with the prediction. Okay, what I mean by prediction is this. if I have a graph, let's say I have a graph like this. Let's say this is exam score. Let's say this GPA. Let's say this is GPA lah. Let's say this is GPA, and this is what we want to put we want to put score lah, not score. Student lah, student. Let me put lah student. This student and GPA. You have a class, and then you want to tabulate the data on student GPA. So you get the data. So let's say you have 100 students, and then you tabulate on this, you get the data scatter. So this is what we call scatter plot lah. So you scatter. So let's say macam mana pula. So let's say I make it clear lah. So let's say you have 100 students, 1 2 3 4 5 6 7 8 9 10 sampai like 100. So you tabulate data. So student A you get here, student B here, C here, here. So like that lah, you get the data. Okay. So this is observation, like we said before. This thing, the data that you put is we call scatter plot. Okay, scatter plot. Okay, this term also coming again and again when you perform the DOE lah. So when you find the mean, you are basically when you want to find the mean, you basically find the average. So let's say this average. This is average mean. Okay, but this thing doesn't predict anything. It's just observation. When you want to when you want to sort of like do prediction, you are not rely on the observation. Observation is just in this case, it's just like you tabulate the data only, student and GPA. But if you try to tabulate the data, for example, so because this you have student GPA, you just like that. But if let's say you want to make a prediction, you must have something that have correlation. So this, instead of student, let's say the data, let's say this student, study time lah, student study time, and then this student study time also, study time. Okay, look here. In the A, let's say I put A here. In A, I randomly put the student. I randomly put the student, what we call, this is not right ni. This student, not student study time, because student study time is, yeah, it's okay lah, student study time. This is random. Wait, student study time. Yeah, this random lah. It's okay lah. This correct lah. Student study time. Let's say here I put randomly. For example, let's say this. Sorry, this is not number of student. This student study time. Let me repeat again lah. So let's say you have this GPA, and then here student study time. In this case, maybe you try to randomize. For example, let's say this is 10, 2, 3, 4, 1, 2, 3, 1, 4, 5, 6, 7, 12. So basically, the student study time on the x-axis is randomized. It's not in order. So you see the data with scatter. You get scatter plot. Now, let's say you change the data on x-axis so that is ordered. So now instead of having random order, instead of this, you try to sort of like what we call to order this data. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say now you order the data. Then the data will change a little bit. Not a little bit, change lah. So the data now, you can see some correlation. So this. You can see some correlation. When you not when you not ordering the data, you don't see the correlation. But now you can see the correlation. Okay. So when you see the correlation, now you can see the correlation. Correlation. When you see the correlation, then you can make prediction. Okay. You can make a prediction. So how you make a prediction here is basically you are making the line. You see the best fit. Okay. You see now the data on B here looks going upward. So you can make what we call the regression line. So you make a regression line that is best fit lah. Okay, no, I don't use the green lah, because green is mean. Okay, before I go to best fit, see this data. If let's say I want to find the mean, let's say I want to find the mean for this average mean, let's say this mean. So let's say I also want to find the mean for this order data. Imagine the A is not ordered, not ordering. I'm not order the study time in the x-axis, but the B I order it. If I want to find the average mean, I will see also the average mean something like this. So this also it become average mean juga. Average mean. Okay. But this average mean, because the average mean will be the same lah. It will stay the same. It's just one number. It's just mean lah. It's just you total all the study number, and then you find the mean. Maybe the mean is 2, 5, 7 like that. So that's what the mean is. This lah, the mean lah. The mean. But if let's say, but the mean here is just the mean. They don't predict anything. Okay, you cannot predict because the line here is not a predictor line. It's just the mean, the average. In order to predict, you need to create a regression line. So regression line is basically the best fit that follow the data. So if let's say I put the blue here, the red here. So if you find the best fit, you get something like this. So this is best fit. So this is best fit. Best fit. So this is what we call regression line. Regression line. So mean and regression line is two different things. Okay. So mean is basically is the same whether you order the data or whether you don't order the data, is the same, because yeah, the same data, the average is always the same. But when you order the data, you can see the pattern. When you see the pattern, you can make a best fit. If there are trend, then you can make a line. You make a regression line. So when you have this line, you can see some. You can what we call, you can see the, you can calculate the distance between your data, true data, and the line. Okay, let me make it bigger here. Let me make it bigger here so that's easy to see. Okay, or instead of using many data, let me put just few data. Let me put here 1, 2, 3, 4, 5, 6, 7. Let's say this data, and then you see the upward trend, and then you want to make a regression line. So this is regression line. Regression line. The distance, okay, the distance between this and this, we call it error. The distance, we call it the distance, we call it error. Okay, so it's not error in measurement. It's just the line cannot explain why there are error. It's not error in measurement at all. It's just the term error lah. Or other term, they call it what? They call it residual. So this is where you heard about the word residual in DOE software, whatever. You can see, always you see residual. This is residual. When they compare the data, the observed data, the blue here is basically observed data. Regression line is basically the best fit. Meaning that when you have line, you have what? You have slope. You have slope. You have something like y equal to intercept. Let's say b plus. In this case, the line is upward, so you plus mx in this case lah. So you know this thing is slope. You know the slope. You have the slope, and this is the what we call the intercept. So you have some what we call some equation for that. So some equation for the line. Okay. So that is the best fit. So the distance between that is, we call it error or residual. Okay. So the residual can be positive or negative. Okay, like before, positive and negative. Okay, and so on. So you can see the residual and so on. So this is the distance. So this is residual lah. What we call residual, like that. Okay, so this is important because so that you can compare this and the mean. Because the mean is other thing. the mean is always the same. When we do like this thing, when we do this, let me show this. Here, you can see here, right? When we do x minus x square, whatever here, this thing, the variance and so on. So that is basically, normally they are working with the data itself, meaning that they are not working with the prediction. Where is the thing? Where is the thing? Let me check. What is the thing? I lost the thing. Yeah, here. Oh, here. Okay. So, because this thing, if you want to find the mean, okay, if you want to find the mean for this, let me put myself here. If you want to find the mean for this data, let's say the same data, the mean is not a best fit. The mean, if you want to find mean, you find the average lah. Even though you order the thing, the mean will be here. So that is mean. The mean. So when you have mean, you also can find the what we call the distance between the data. For example, you can also find the distance between data, and this is what we call what we deal with the variance. When you find the variance, variance is basically the sum of your data meaning that this lah the observed data, the blue dot, the data minus the mean, oh, I put in this lah, I put in this thing, minus the mean, okay, and the square. We learned before in the previous video that we square, because if not square, then the positive and negative cancel out, and then you divide with the number of this thing. Okay, so that is variance, and if you want to get the standard deviation, you divide, you square root lah, because this square, you square root. So this is variance. So here is this is when you deal with the mean. Regression line, when we talk about residual and so on, this what they talk lah. They talk about, they try to make best fit. They try to predict your data. For example, let's say you do this experiment, they will say that, okay, next time you do experiment, if you change this and change that, then you will get this. Based on what? Based on this regression line. Okay, the lower the residual, meaning that if let's say this thing, if the residual can be positive, if let's say the data, the blue dot here, is on top of the regression line, is positive. If the data, if at the bottom, then it's negative. The lower the residual, meaning that the lower the residual, meaning that there are less difference between the regression line and your observed data, the better lah, the better predictor lah, meaning that your data, whatever predicted, will be almost always correct. Because if let's say you have something like this, you have data, you have something like this, and then you have data line very nicely like this, and then you can make the what we call the regression line exactly on top of the point. So this, they are no residual lah, meaning that whatever predicted later on will be exactly, meaning that whatever you observe, the regression line, the equation that is developed, is true for next time. That's why when you see something like this, normally you can see in spring constant. For example, you have a spring, you have spring. You in the spring, when you look at the equation for the spring, they are spring constant K, I think, the Hooke's law. Why they call it law? Because the data is almost always the same, and the regression line all match the data. It's always be like this, cantik, they always clean. So that's why they put as a law, because they never change. But if your data is like this, for example, most of the time when you do experiment, the data will be something like this. Your data will be scattered here and there. It will not show the perfect correlation. This is what we call perfect correlation. Perfect correlation, where the data, where there are no residual, where there are no error between regression line, and also you observe. So it's just in one thing lah. So that's perfect correlation. When you have perfect correlation, then you can make a law lah. This thing always true lah, because you can predict. Whatever you predict is always same lah, because you observe, and prediction is the same thing. But more often than not, you have something like this. You have something, the data scatter. So in design expert software, they will tell you the residual here, the residual here. The lower the residual, the better the prediction. Okay, so that's the thing. So the R square coming from where? R square coming from this lah. From the R square is basically the term R square. This is basically the variation of the mean over variation of this is basically variation of the mean minus variation of the line over variation of the mean lah. Variation of the mean. So you know the what we call the mean is this lah. The mean is this. So basically, if R square is 1, what does it mean by R square is 1? R square equal to 1 is basically this lah. When you have perfect correlation lah. Perfect correlation. Okay, so that is basically what does it mean by R square equal to 1. So if you have lesser and lesser, meaning that your data scatter compared to the predicted line. Scatter far away from the predicted line. So that's basically what does it mean by R square. You will see this during when you do ANOVA analysis. They also give you also the R square. They also give you how far your data, how true is the prediction given. Okay, so that is the R square lah. Okay, so until now, okay, so that's prediction. So this I just show the term lah, the term. Okay, so now let's see the statistic part. Okay, so the Z score and T score we see before. So they just T distribution and Z distribution lah, and so on. The confidence level, alpha, p-value we have learned before. The t-test, I will not cover lah, but it's basically it just you use t-test to compare between two group. The T, there are many things, but the same thing lah. The T, there are t-test, t-score, whatever the thing. But we not go in detail. Just it's related to f-value. Like we talked before, f-value is needed in order to to perform the ANOVA. So as you see before, this f-value is basically between group variation versus within group variation. Okay. So yep. So the high f-value means that there are a lot of variation between group. For example, the way to look this is like this. Let's say you have two batch of chemical. Let's say you want to perform what we call experiment, and then you want to mix two things. You want to mix A and B. You want to mix A and B, and then both A and B you buy from the supplier. You buy A and B from supplier. Okay, but in order to conduct this experiment, this mixing experiment, you mix this A and B. In order to conduct this experiment, maybe it's not enough. Maybe it's not enough for you to use just one batch of sample. Okay, let's say you buy inside you buy this A and B inside one batch lah. You buy one batch. So you found that when you want to perform all the experiments run, it's not enough for you to use this entire batch. You need to buy another one. But unfortunately, that company, maybe that supplier, the supplier that supply you A and B thing, doesn't have anymore the AB. So you buy from the other company. So let's say this, company 1, you buy from the company 1. This you buy from the company 2. So this is where this between group variation and within group variation is happen lah. Because the variation between this, what happen in variation, the variation will happen within within this material given by company A, and the variation might also will happen between the material that's given supplied by company 2. There are variation within the material itself, but also there are also variation between the sample. Okay, So the F value, they find this between group variation versus within group variation. Normally the within group variation, so this within group variation normally less because you use from the same company. So normally the variation of data or whatever normally less, but they might have the significant variation between different supplier. So if you have what we call low within group variation, meaning that that is ni lah, within group, between group. So if you have, like, say for example, there are a lot of variation between different supplier, then you have this, the top one high lah, mean giving the F value high. So that's what does it mean, the F value lah, in rough idea.